Hi, welcome to ToddFun.com, and today's fun is I'm going to start on a frequency counter for an old ham radio, a Kenwood TS520S. It's an older style radio that does not have any displays of any kind. It's all dial, so they call it a boat anchor, but it's really a very functional HF ham radio. A friend of mine has it. He got it for just not much at all, sub $100 or something like that for the whole rig. But he's got issues with what frequency he's on. There's a complicated procedure for getting the dial calibrated so that the dial is reading the little tick marks, say you are where you actually are transmitting on or receiving on. Now, I believe I can make a frequency counter, this digital display frequency counter, with an Arduino. And this is an excellent project for an Arduino, provided I can pull off this little trick, because it lets me lash up an inexpensive development board where I could program this Atmega 328 with code necessary to interface with his radio and calculate the frequency he's receiving and transmitting on, and give him a nice display on an Adafruit LCD shield. Backlit, multicolored, RGB LCD shield by Adafruit. That's what I'm going to put the display on. And it should be easy to see in the ham shack even when it's dark or dim, and he can control some features depending on what I program these buttons to do on there. Now, if you don't know what an Arduino is, it's a development board with a programmable microcontroller chip on it. It's an easy pre-built development board to use. You don't have to build it yourself. It's about $30. You plug in USB and or power. If you've already coded it, you can just power it. But if you're coding it or using it, you can hook up your USB. And then you write code that use these header pins as inputs and outputs to either control things like motors or lights, or inputs for like frequency counting. So if you don't know anything about Arduino and this cute little development board platform, there's an entire community behind it. Go to arduino.cc and start reading. Specifically, you download the IDE, which is the development environment software for coding this little board. You get the board and a cable, and away you go. And start following some of their samples, and they have an entire playground there. You can click on their playground and try and other things, and or submit your own work. And there's tons of examples out there. Now, Adafruit has a lot of tutorials that are really good, so go there for some Arduino tutorials too, and some libraries, specifically the LCD library for controlling this board that they build. But there's other libraries. Other people share code libraries, so you don't have to write all the code yourself. I'm going to be using a frequency counting library specifically designed for counting frequencies. And I'm going to share a link in the show notes as well at ToddFun.com for this post on where I got that library. So I don't have to write that either. I just have to use basically some snippets of code to do a portion of my work for me, both for controlling the LCD and for doing the frequency counting on the Arduino. So in order to do a project with my Arduino for this application, I have to know a few things. I have to know what my Arduino can do and can't do. You get more comfortable with that as you use them. You have to know what you're interfacing with. In my case, I'm interfacing with a ham radio. And through some other research, I found that you can get a digital frequency counter for this old radio. They had the one for the radio, it was designed to use one, but you had to pay extra for it. I think it's called a DG-5 add-on. And it gave you that pretty much necessary frequency display to make using your radio just nicer. And so the radio has outputs on the back. They're RCA outputs, and they output 3 frequencies, and I'll show those on a whiteboard and what the importance of those are. and it uses those three frequencies. It measures those three frequencies that come out of those ports to calculate what frequency the radio is tuned to for transmitting and receiving. I believe I can mimic that internal to the code of the Arduino, provided I can properly measure the frequencies coming out of those three RCA jacks. Now, I'm not basing any of this on I know everything about ham, because I don't. I've only been a ham for a couple of years. I'm still learning a great deal about it. But I do believe I've done enough research, hopefully, for how the DG-5 works to understand how it's using those three outputs to calculate the frequency. And if I'm wrong, well, we'll see if we can correct for that later in the video. And if I'm not wrong, then it should just work. So here's what I got. I measured one of them. Is called the VFO, Variable Frequency Oscillator, and it's putting out a nice clean sine wave with about a 0.3 volt peak to peak. It's going from about 4.9 to 5.5 megahertz, depending on what band you're on and where you're tuned where you tune all the way, basically tune all the way to one side and all the way back to the other. And then I repeated that test to see what the BFO, beat frequency oscillator, was. And it was a 0.4 volt peak to peak sine wave, nice and clean. And it pretty much stayed solid at a little over 3 point some megahertz. But now this can drift a little bit, and we do want to measure it fairly accurately so that we can do some calculations. And then the HFO, I believe it's also called HET, but here I'm calling it HFO for high frequency oscillator. And it's producing a high frequency of about 0.5 volts peak to peak, 10 to 40 megahertz. Now, from what I've researched, the frequency you're transmitting and receiving on should be the HFO minus the addition of the other two. Well, let's hope. Maybe I don't have that right. Maybe it's more complicated than that. But, you know, I don't have anything else to go on but that right now, and if it doesn't work out, we'll find out quick enough. So, does the Arduino measure those frequencies outright? Well, first of all, the inputs are pretty low. We're talking, you know, half a volt and less. And no, we will have to do some amplification to these sine waves. So that will be our first circuit we'll have to build outside of Arduino to amplify these up to close to 5 volts. And I'm really only interested in square waves that represent this frequency, so I'm going to probably try and chop these into nice square waves, 0 to 5 volts, without losing their frequency. At that point, once we've done that external to the Arduino, yes, I have done enough looking into the Arduino. The Arduino can measure up to 8 megahertz, provided you're clocking the Arduino with a nice crystal like the Arduino has at 16 megahertz. That is, the Arduino clocks at 16 megahertz with an external crystal that's on the board. So you can pretty much take that and divide it by 2.5, and that's how high you can count. And now 8 megahertz is a little higher than that, so that's pushing it, but these are lower than 8 megahertz by a significant amount. So for two of these inputs, the VFO and the beat frequency oscillator, I can basically, once I've conditioned those signals to be at least the voltages I need, then I can go ahead and count them. And I'm almost done then. I just have this big 10 megahertz to 40 megahertz signal for the HFO. Now, my plan there is to still use the Arduino, but I'm going to do a prescaler. And what that means is I'm going to divide that frequency by a scale value before it gets to the Arduino. So when the Arduino gets it, it's under that 8 megahertz limit. And then some, actually. So for my prescaler, so I can measure that higher frequency with the Arduino, I'm going to, first attempt is going to be, I'm going to try and use a CD74HC93, which is a 4-bit binary ripple counter. Okay, it's 4-bit, but I'm going to use it in what's called the 3-bit mode. That's because I want divide by 8, not divide by 16. I don't need divide by 16 at any time. So, might not get away with this because per the data sheet, I might start having problems at about 20 megahertz with this chip. And if I do, there is other chips out there similar to this, binary ripple counter that go up to like 60 megahertz. So I'm really, I might have to change the chip, but the concept won't change. So what's going to be happening is, to make the math easy, I said, well, here's our input, and we're going to say that's 32 megahertz, just because it makes the math easy. So I'm saying input is 32 megahertz. Forgot my Z, sorry. And that's clocking along at 32 megahertz, and I've cleaned it up and made it nice and square, so the Arduino is ready to count it. And that goes into this counter chip. On the output of the counter chip, it's going to put out a pulse every 8 of the others. So it's going to divide by 8. After seeing 8 of these pulses, it switches position. After 8, it switches position, so on and so forth. So this frequency coming out will be 8 times smaller than the frequency going in. Right down to just, very accurately, actually. And so that I should be able to get like 4 megahertz, forgot my Z, sorry, going into the Arduino. And like I said, if that chip doesn't work, I'll find another chip that does do that same concept. So then I'm left with really only one other task, and that is the library I'm using and the way the Arduino is going to be set up to count these frequencies. I'm going to be using just one input pin, but I've got 3 frequencies to measure. So I'm going to need one more chip, essentially a select chip. Now for that line select, my plan is to use a CD74HC153, and it is a 4-to-1 line selector, or essentially a multiplexer. It's if this is the Arduino and it wants to have those frequencies come in on this one line, and they are your VFO, BFO, and HFO, I can go through this multiplexer, and by outputting either highs and lows, combinations of highs and lows, on these 2 lines, I can multiplex which one of these is coming through and getting to this counting pin of the Arduino. Without getting any more into it than that, I don't want to complicate it right now. I should be able to use that single input to count all 3 and then do my math. Now, you start multiplexing and so forth, and you start slowing things down. But I only have to be accurate to probably 100 megahertz here for this to work well, because that's about all the more accuracy he would need to be on frequency. Which means that the counting and the resetting of the counting and the multiplexing can go fairly fast. Now, for the calibration and the testing and the proof of concept for the rest of this, I'm going to be trying to get down to a single hertz, because I want to be able to make sure that I am counting based on using some of my high quality, high precision counters, make sure that my Arduino is giving me dead on numbers. That way it's calibrated to be dead on, and so when I let it go and free run a little faster, I don't have to worry about it free running from a point in which it's not doing a good job. But then it should, when I let it go faster and not be precise, essentially open the gate up a little bit so it can do more counts quicker. It will be able to do all this complicated multiplexing and counting and calculations, and still be perception to human still fast enough to seem like it's just going, without hesitation. And if not, I hope it doesn't slow down too much, but we'll see when we get to that. Now, to the bench to do some proof, to get to some actual circuits. Let's do our first thing, which is counting, making sure the Arduino can do straight up input counting of a nice clean frequency within the range of the VFO. And then we'll do the BFO, and then we'll do the harder one, the HFO. And then we're going to combine them with the multiplexer. And then the final step is going to be making sure that we're amplifying and signal conditioning however necessary, because I'll be able to make some shortcuts here, so that everything can flow through all those chips to get to the Arduino. So we're going to do this one step at a time, sort of modular, and so I hope you follow along all the way to the end. So this is how simple the setup is for testing the direct measurement of the VFO and the BFO, because those are within the 8 meg levels actually quite a bit under what the Arduino can actually do on its own. So the Arduino has two inputs, has a ground and a signal coming into a couple of input pins, and then of course it has the UBS to the computer for programming and monitoring. Then over here we have my signal generator, and it's outputting a 1 meg signal sine wave right now. I guess I could turn that to a square wave, wouldn't hurt either way. And I've actually got a T on here so that I can go down to the Arduino and over to a counter. So I can confirm that the Arduino is counting the same. Okay, and I have a few counters here so that I can cross-check them. So I have my leader, and it's actually flipping between 1 meg and 9999999. Okay, and so it's basically saying, yeah, my frequency generator is outputting fine. And then I have this HP counter, which is a high precision, and we'll turn that on. It's actually staying warm in standby right now though, so we'll leave that there. And it's much accurate, and we're going to use that too. So we'll turn that on. We'll pull that out and we'll stick it into speed, and it doesn't show up on the camera very well because of the frame rate, but yeah, it's basically about 1 hertz under what the leader was saying, 1 cycle a second under. So these two units are agreeing, and that's good enough calibration for me. Plus I only have to be within 100 megahertz to make this work anyway. So this makes a lot of noise, but it does show the accuracy, but we'll just leave it in the heated mode standby while we use the more quieter leader. Okay, so that guarantees that we got that. So then what do we have going on for the computer? We have, and I'll just let you see, that's the site where I got this library from for doing the frequency counter. It's at Art Academy, actually in Germany, I believe, and they were kind enough to share their frequency counting library. So all I really have to do is call their library, which I downloaded and put in my Arduino library, and then all the code is for the sample code is here, where it just declares a long variable, a count that is how many times it actually counted a frequency. So it's kind of useless to me, really. A pin to flash an LED every time it makes one of these counts. So really this is the number I need mostly, this frequency. And then it's going to set up that pin to flash, and then the output for the serial port so we can see what Arduino is doing without having a display on the Arduino. And then it's just going to print the word frequency counter, kind of unnecessary. I have to scroll. And then that's the end of the code, actually. We've got the loop, where it's going to have a calibration number, which I put in 91, and I dial that 91 in, following the instructions on their site. It starts off at 100 for this gate. If I'm using a 100 millisecond gate time, you're supposed to use 100 here. But then you start going up or down until your precision voltage counter agrees with what the Arduino is doing, because the Arduino will have its own little error, if you will. And this is the 91, gives me almost no error across all the frequencies that I'm going to be measuring. Then it does a while to make sure it's ready to get a frequency from its little library. Then it actually goes out and grabs one of those frequencies from the counting pin input, puts that in FRG, and then increments and outputs the counter so it knows that it counted one, and then it says the word frequency, puts out the frequency it counted, and essentially flashes the LED, delays 20 seconds, flashes the LED, and goes back up to the top of the loop. And that's really all this is going to do, and that's what I'm going to augment and make more advanced for doing all 3 frequencies and controlling the multiplexer and stuff like that. So there'll be more code in here in the end. I won't cover that anymore in the video. I'll just share it at the end, however it works. So now it's actually counting and it's actually hooked up. So let's go over to we're here in the Arduino integrated development environment, and it brings up a monitor, and that's what's coming across the serial. So it does a reset to the Arduino, and then the first frequency it read was 0. because it was just reset the Arduino, and then it was a little, it didn't stabilize. And then this is what the Arduino is reading on the input pin. And you can see it's actually almost perfectly agreeing with the HP, right down to a single hertz. So this is very accurate. Now I got a wide gate. I got a 100 millisecond gate, so it gives it a lot more time to get a good reading. And I don't need this level of accuracy, so I'll probably turning that gate down quite a bit so that it actually responds faster. Which means I'll have to have a different calibration number, but I can get those numbers later. That's not a problem. Now I've dialed the frequency generator to 3.395 megahertz, which would be right about where the beat frequency oscillator is, and this still is going straight into the Arduino. And the leader is reading 3.39, almost 5. It's just a single decimal off. Let's try the HP. Once again, the frame rate is kind of messy, but 3.39 and 4.98. So right in there, even with the HP. Now I know I don't have everything terminated properly with 50 ohms, but I did do this measurement with the 50 ohm terminations everywhere, and I did get exactly the same number. So even though I'm not strictly sticking with the termination, I am getting proper counts. Now this is the high end of the VFO that I have to be able to read with the Arduino, and I'm getting 5.5 megahertz. Just a tweak over 5.5 megahertz, and that's what the frequency generator is outputting. Let's see what the leader says, and then we'll go see what the Arduino says. Or the leader is agreeing with the 5.5 megahertz. Now, if the Arduino agrees with this, including the 0.98, we're really accurate. And here's the Arduino running, and it is agreeing with it. 5.500981. So it's actually giving me one extra digit of resolution than my leader, and they agree all the way down to the 8. So we are good to go with counting the VFO and the BFO. Now we have to test using the prescaler for larger frequencies. But I do have a problem. My frequency generator doesn't go that high. My frequency generator only goes up to 7 megahertz, which isn't going to test my 10 to 40 megahertz. What will I do? Well, my attempt, being I don't have any other frequency source, I'm going to try and use this MFJ SWR analyzer, this antenna analyzer, which does generate frequency pulses, and I can use the 10 to 26 megahertz range and the 26.2 to 62.5 megahertz range, and it'll output it through this BNC jack I have. And I may have to amplify it and do a little conditioning, but we have to do that with the HF rig in the end anyway, so I'll need that circuit in the end anyway. And if it's strong enough source, I should be able to use it straight off. So we'll see. This will be my 10 to 40 megahertz generator. And we can also calibrate and make sure this thing's right using my HP. This is the 10 megahertz output from this SWR analyzers, MJF. This model is MJF 259. I'm using it as a signal source and 10 megahertz. And my oscilloscope is saying, yeah, that's good to go. I can go up to the next range. Now this button is kind of tweaky. Now this button is solid, so when I'm on the 10 megahertz range, it's solid. In fact, when I'm even, down in the 2 to 4, it's I wiggle this button and crazy stuff happens. So like that, it's just holding on the 26 to 64, and it's doing 25 right now megahertz. But if I can just hold it like this, I'll just tweakle this. I'm just gonna wiggle this button, and that's just I'm not even turning it. I'm just applying pressure to the button, and it just I've actually seen it go completely away. There's upper range, it's pretty solid. Back down to this one, it even kind of clips it a little bit sometimes based on how so this contact must be dirty in here. But if I even go up a range, it's really solid. Up another range, and up another range. It's still pretty solid, so it's just that one wiggy range. But it's going to give us a clean enough signal for what we're doing. We don't have to bother that much. But I have to tell my friend that his SWR analyzer is a little wiggy on that range. So this is going to be the first, but granted we're seeing the megahertz up here, but we're only getting a 2.2 volts peak to peak. I'm thinking I'm going to have to amplify that signal already before I can use this as a signal source, which I have to create an amplification circuit anyway for the radio. I have to amplify this signal before the Arduino is going to count it. But let's give it a try. First, let's hook it up and see what the frequency counter is actually saying. This is pretty much right at, I'll just turn it up a little bit more to get out 10 megahertz. And you can see it's tracking pretty close. This isn't a real accurate, stable generator. It's reading 100, and it's tracking real close to that. So if whatever this is reading is accurate, and if the Arduino agrees with it, then that's what counts. Well, just as a sanity test, I hooked up something that the Arduino can read, like somewhere around 5 megahertz. It should have no problem reading. And I got this cable going directly into those same pins that it would read if it were at least a 5-volt square wave, and it's not getting anything on the screen over here. So if we can scoot over here to the screen, we can see it's just driving in zeros. So we need an amplification circuit for sure before we can use this signal source, and then we need the prescaler if we want to go higher than 8 megahertz. That's the next test. Before I build my conditioning circuit for those those smaller signals, I want to try out my high-speed CMOS 4-bit binary ripple counter, and I'm going to put it in 3-bit mode, which means I'm going to have a divide by 8 coming from Q3 here. And you can read the data sheet for this part if you want more information. So I want to do that first just to make sure my divide by 8 chip is working. So I'm going to start off with, because I'm going to be using high impedance anyway, I'm going to go ahead and just I'm going to do a test here with a straight cable. I'm not going to go into my 50 ohms because I'm going to be going into a high impedance Arduino anyway, so I just want to know what the loads are going into this high impedance because that's what I have to measure anyway. I got my signal function generator set up for 4. Well, it's a little hard to see, but it's set up for 4 megahertz. But I do have it set with an offset. So, and I have dialed that offset to 0 for the low, and I've dialed in a square wave, as well as an output amplitude of 5 volts from 0 to 5 volts. So I got a nice square wave, but as you can see, not so square because my function generator just can't do it. I do have bandwidth limiting on right now. If I take it off, you can see it's a little noisy. And this is 1 volt per division, so that's 5 volts. The frequency is 4 megahertz. I can show you the ground rail right there by clicking that. So now I can show you that my ground is right there, and so you can see it is a 5 volt square wave, or as square as my generator can produce. And the point of this is so I have a nice strong signal to put into the divide by 8 chip, and then the Arduino can show that it's dividing by 8. And if all goes well, of course, what's 4 megahertz divided by 8? Should get 500K. Just for the convenience of the setup, I'm going to go handheld. I got the 4 meg square wave, 0 to 5 volts coming out, going into the oscilloscope with a splitter. Don't yell at me for this. I know it's ugly, but it's just for demonstration. So then another splitter down here. One goes off to the Arduino inputs. Actually goes into the divide by 8 binary ripple counter, which then its output goes into the Arduino counter. So it's divide by 8 frequency should come into the counter, and because this is 4 megs coming in, it should be 500K coming over to the Arduino. And the Arduino can do some math to multiply that if it needs to. Well, of course it will. And then coming up here, we have, just to show that this is also, this is really accurate, showing this is a 4 megahertz. So yes, we should get 500K divided by 8. And then over here, the Arduino's got its UBS coming out here where it's getting power. I have a common ground for my dev board here. And this divide by 8 is getting signal here and output there, and 5 volts power from there. Interesting thing about the 5 volts, I'll show you in a minute. And over here, lo and behold, the output from the Arduino is showing 499.998K. And if you multiply that by 8, you would get 4 megahertz. And that means it is working. So as long as we can condition our input signal to be in that range, this divide by 8 chip will work just fine for us. So we can go ahead and start working on our signal conditioning circuit. This is what happens when you overheat a chip and melt it, and you melt all of your pins, and then you have to grind it out and fill it in with epoxy, so you don't have a hole in your board. So the interesting thing with this is the 5 volt power supply coming from my to power essentially this chip. But watch this. I found this out just by accident. I unplugged my chip. I have no power going to my chip, but I do have 5 volts, a 0 to 5 volt signal coming in from my function generator into the input pin, not to the just to the input of the signal, not to the input power in. And even though I have no power to my chip, look, it's still counting just fine. So that input signal is more than enough power to power the chip. Isn't that strange? And for a level of completeness, and to say that I've used every piece of equipment again, yay, I hooked another, I tapped into the same output of this divide by 8, which is what goes over to the Arduino, with this cable, and this cable comes up and around, don't get sick on me, and goes into my HP. And look at that. Boy, the frame rate is really messing with you guys, but it reads 499, so 499,997 is what I see with my eye, but your frame rate, you're probably missing a few digits coming and going. And still the Arduino is counting those divide by 8s, and it's within 1 hertz. So that is very accurate. That Arduino is definitely going to have no problem. And I could, of course, easily write a piece of code to multiply that by 8. So yeah, let me do that real quick. Okay, I've done a times 8 on the frequency right before it puts it out to the screen. This code is then redumped to the Arduino, so the Arduino is then running this program and outputting this number. So it's taking it and multiplying it by 8, and we're getting 4 megahertz. That's the 4 megahertz coming out. Now, if we come up here, we can see that this is the same output from the actual function generator, and I mean, they're really close to, and this is in K as well. And so that is also right on 4 megahertz. So it's got an extra digit of resolution there, so you get to see the 8.4. So yeah, very easy to compensate for that, to produce that scalar and compensate for the Arduino's input frequency limit. Okay, it's getting to be a lot of content. I don't want the video to get too long, so I think I'll call this part 1 and wrap it up and get it edited and out to you guys, so you know where I'm at with this frequency counting project. Join in for part 2, which is going to be the signal conditioning, so that I can get those weak signals, those small signals up to I don't have to get them square waves. I just have to get them. I just want to clean them up as square as I can and get them from 0 to 5 volts as close as possible, because that's what the Arduino is going to like the best. Though it's not necessary. I just want to get there as close as I can with those input signals. And as long as I have this SWR analyzer, which outputs almost identical signal, once I get that conditioning circuit for that, then my conditioning circuit should be good to go for the 3 outputs from that ham radio that I need to measure. And then the multiplexer has to come. I have to write some multiplexer, and then I have to speed it up. I have to change it so it's not sitting there and taking a measurement every second. I want to speed it up so that, yes, at that point the accuracy will fall away, but I don't want it to fall any more than, I want it to be accurate within 100 hertz, which is fine for ham radio work. And of course then it'll be faster, and then of course that'll be the true test. Take it over to my friend's house and hook it up to this radio and see it working, and hopefully it'll be everything that we envisioned it to be. Thanks for joining so far.